This is the start of the diagnostic section. It's going to be for variable valve timing. It'll apply to both the early Vanos and the newer systems. These are the systems that will be using the latest version of variable valve timing. It's the one we're going to have the service codes for, and this is just a partial list to give you an idea of what's going on. This is going to work on the BMW double Vanos. This is a second generation of valve timing. The Ford variable valve timing on their later models uses variable valve timing. GM continuously variable valve timing is their name, and will be using it. The Honda VTEC. The I is unique. It is not a standard VTEC. This is for their economy model cars, not their performance like they have for the VTEC. It is a subset of VTEC and does not function at all like VTEC. It uses variable timing, as we've been discussing. The Hyundai and the Kia use continuously variable timing on all of their new cars. And the Mitsubishi Mavic is one of the most advanced systems. A part of it is variable valve timing. They have more features and have done a number of innovative things in their variable valve timing and are one of the leaders in this in the Asian market. The Nissan continuously variable timing, and again, they have several innovations. This was just the variable valve timing portion of their program. As with Toyota, theirs is called variable valve timing with intelligence. I think that's a slam against Honda, saying that the Honda VTEC wasn't very smart. The Volvo continuous variable valve timing, and then we've got Volkswagen, and we've got Fiat, and we've got all these others. Every manufacturer is doing it. It's only a matter of which models. Within the next 2 or 3 years, every model is going to be using variable valve timing because it's inexpensive. Now, what we've got to talk about is how we diagnose it, because the diagnostics are an important part of this. The first thing to do with anything is to check for codes. Now, we're going to divide these codes into groups. We're going to talk about the actuator circuit problems. Now, these 4 codes you're looking at are for exhaust and intake. They're bank 1 and bank 2. They all have one thing in common: the actuator circuit problem. So what we're going to have to do is break these down into pieces. Utilize this for these codes. We're going to show you how to diagnose these. What actuator circuit problems means is that the PCM has determined that the voltage signals do not match the expected values. In some rare cases, it's going to use current flow. Mainly, they use voltage. We're going to teach you both of them. Now, the control voltage is determined by whose system it is. One thing we should have made abundantly clear with all the variations here is not everybody does it the same. GM does high side switching and supplies B+ to control the solenoid. Almost everyone else uses low side switching. Ford is our example. We have schematics for GM and Ford we're going to be using to demonstrate these two things. And you're going to need to use a diagram to determine what type of control is being used. This is a ground side switching from our Ford. Now, it's unlikely you're going to find a diagram that shows the internals of the PCM like we have here. We did this for training purposes. This is our drawing, and you aren't going to find one like this in the marketplace. No, we don't have enough man hours to draw all the drawings over, and you don't want to pay enough money for us to do it all. But that's the answer to the question I get all the time. Here's the diagnostics. We see that the computer is going to supply ground. That means the computer grounds at the bottom have to be good as well as everything else. Bad grounds on a computer can cause strange problems. They're not going to keep the solenoid from working, though. They'll cause the computer to act up. Ground side switching is the most common. We're going to go there. We have power supplied from the battery. In this case, it's a Ford. It comes from the PCM power relay, better known as the EEC relay, whatever you want to call it. But a number of manufacturers have arrangements like this. But what we've shown here is enough of the diagram. You can see it shares power with the injectors. That's the important piece of information we're trying to show here. The way you determine you have ground side switching is finding one side of the solenoid going to battery voltage. You know the other side must be for ground side control. Doesn't matter which we're supplying ground to turn it on or supplying B plus and ground the solenoid all the time, which is what we do when we change things. Now we're going to give you some ideas about these and get some specifics. Ford has a resistance of 3 to 6 ohms in their actuator. If we go and supply ground to pin 44 with battery applied to the other side, we will draw between 2 and 4 amps depending on what the battery voltage is and what the resistance is, the two ranges. Now we're going to be using this later on. When we look at duty cycle, it's going to be important. If we want to understand how this circuit's working, we look at voltage and duty cycle and amps, all three. At 50% duty cycle, I'm going to have 50% of the maximum amps, between 2 and 4. There's 3, I'm going to have about 1.5 amps at 50% duty cycles. So if 3 is the average, half of that average is going to be 1.5 amps. That'll be the average amps typical of what we expect to see. When we see 50% duty cycle and 1.5 amps, we know 100% that the EEC power relay, the red wiring coming up on the left, the control circuit, the PCM, and the grounds at the PCM are all working normal. Let me say that one more time because we're going to talk more about it when we get into diagnostics. But I want you to stop and recognize it here. When we see the 1.5 amps and 50% duty cycle, we know that all the circuitry is working. If we've got a problem with a code, don't worry about the circuitry. It's either in the actuator or it's in the phaser. And we're going to show you how to decide if the phaser and other things are bad. High side switching works just the opposite. GM is the predominant one utilizing this. They switch off and on with 12 volts, and the other side of the solenoid is always grounded. There is no switching. When you see a solenoid like this, you'll frequently see it going out to a ground, or this circuit on the black wire will be labeled return. In that case, it is not a control signal. The control signal is at the top. GM's variation, and we're trying to make sure you understand variations. Their coil resistance is 8 to 12 ohms. The average amperage is about 1.2 amps max. So at 50% duty cycle, we expect to see half of that. Between 0.5 and 0.75 amps, let's say we had 0.6, we'd be right in the middle. That says that all the circuitry is working normal. Now that's very important to us because we frequently see 50% duty cycle. It's the most common duty cycle you will see when measuring this. And when you see that and you measure the amperage, you know the circuit's all normal. Let's talk about other things we got to do. As we've just shown you, the resistance can vary by manufacturer, and you determine the maximum current flow by doing a current draw test. If you have to, disconnect the actuator and use a jumper wire and power the actuator to measure the current. If you do that separately and the maximum current can be reached, the actuator resistance is normal. Now we're ready to use that as our diagnostic baseline for the 50% duty cycle. The duty cycle changes the average voltage, so we can also use voltage. Now what we're trying to do here is to show to use duty cycle, which you're going to get out of your scan tool in some cases. Not all scan tools always display the variable valve timing duty cycle. If they don't, use a voltmeter. Duty cycle causes the average voltage to vary, so we can also use a standard voltmeter. If I have 50% duty cycle and I'm looking at battery voltage of 14 volts, I expect to see around 7 volts here. It's that simple. 7 volts, 50% duty cycle tells me this circuit's working. Now, let's move on down here. Causes the average voltage to vary. That's very important. We're going to talk about that amperage again. Amperage is a more advanced way of testing it. And if you can use an enhanced scan tool that shows duty cycle, use it. GM at 50% duty cycle, we just said, is going to be between 0.5 and 0.75 amps. Voltage is going to be 6 to 7 volts. We've got actual numbers. Now, you can apply the same principle to that whole list of manufacturers we're looking at. When you got 50% duty cycle, it's going to be half the maximum amperage, and we just show you how to calculate and measure the maximum current flow in the circuit. If you can't get them to verify, if they don't match, if current, voltage, and duty cycle don't agree, then you're going to have to do circuit testing. You may have unexpected resistance. Now, the voltage levels we're going to be seeing, we look at ground side control, for instance. When we're at 100% duty cycle, it's going to be under 1 volt. And we're going to be at B plus when duty cycle is 0%. Now, this is frequently, multimeters have plus duty cycle and minus duty cycle. All of this is related to minus duty cycle, the time the voltage is below 1 volt. So we say it like that, the time the voltage is below 1 volt is 100%, we should be under 1 volt. We should be near V plus if we're never down to 1 volt. Makes it easy to understand. High side switching, if we use the same thing, your scan tool may show it the opposite of this. It may be absolutely inverted because we could be using plus side duty cycle. How much time are we at battery voltage? But on ground side switching, using the same setting, B plus would be 0% duty cycle, and under 1 volt would be 100. 100%, we're always down at 1 volt. Pay attention to your scan tool, understand what you're testing and how to use it. And if you have a scan tool with bidirectional testing and you control it and watch the duty cycle and voltage, do it. Here's some typical failures and where to go. We're going to talk about them. We're going to take a schematic and see how to make these measurements. So we're going to tell you what we're going to tell you, then we're going to tell you what we told you. Because we want you to really understand this, because this can greatly reduce your diagnostic times on these critical systems. If the voltage is always B plus, check for an open in the control wiring or an open driver. Now this is all depending where you're checking. If you're checking out at the sensor or at the actuator, you've got a lot of wiring between you at the PCM. It's very unlikely you can go right to the PCM. It could be an open driver. Now, an easy way to decide that, we'll show you when we get to a schematic, is to simply do a max current test. We'll show you how to do that again, remind you how that works. On ground side switching, if the voltage is low, it's always low, we're going to check for an open in the B plus wiring or a shorted driver. Now, let's take the time to go look at a schematic and see exactly how we apply these simple rules. Here. Right now, we're measuring at pin 44. We do that to eliminate a lot of steps. If it's always low, check for an open in the control wiring or an open driver. Well, we're pretty close here. If it shows B plus at 44, there is not a lot of circuit left. My suggestion is take a jumper wire, supply ground to pin 44 right there. If you draw a normal current flow from max amps, all the circuitry to the left is working. Let me say that again. If your amperage reaches the maximum value, everything to the left, the violet green, the pink and blue, the solenoid itself, the wiring on the red, back to the power system, all of that's normal. If you draw a normal current flow, you have an open driver in the PCM. We said we're going to try to make this simple. Now, if the voltage is always low, you better check, make sure you got B plus first thing. If you got B plus first thing and you don't have an open in the actuator and there's no bad pins on the actuator and the circuit's all good, you probably have a shorted driver. If you disconnect the wiring at pin 44 and it jumps back up to normal voltage on the control circuit, the driver is shorted. It's that simple. Keep it simple. Don't make this complicated. High side switching works very similar. except it's going to be reversed. If the voltage is always B+, check for an open in the ground wiring or a shorted driver, because the ground has to be there in order to be able to have normal voltage readings. If the voltage is low, check for an open in the B+ control wiring or an open driver. Going to the schematic, it makes it really obvious. Voltage always high, always B+. Check for an open in the ground wiring. We've got to have a good ground for the circuit to work properly. Most likely cause, that driver is shorted, always giving you 12 volts. This is fairly simple. We do not want to make this complicated. Now, if the voltage is always low, check for an open in the B+ control wiring. Now, if we're back checking at the pin C239 in this case, and we don't see any voltage, it's almost guaranteed it's the driver. If you want to verify it's the driver, you can apply 12 volts right here, see if you draw normal current flow. If you do, all the wiring and the actuator are normal. It's internal to PCM. Simple diagnostics that get you to the root cause of the problem are the most effective. Now, if we have excessive current flow, it indicates a short circuit, and we're going to have to go check circuit integrity. Low current flow indicates extra unexpected resistance. Now, we use the term high resistance, and I do it reluctantly. In this kind of circuit, we're drawing 1, 2, 3 amps. 1 ohm is exceptionally high in this case. We do not believe in using resistance. We believe in using current flow. So keep that in mind. Try to find where you've got unexpected resistance. Connectors, the actual actuator itself, bad grounds, wherever it may be. Now we're going to do something here in the second part of this we're going to use for more diagnostics. We've been using these jumper wires to do some measurements and activate it. What we're going to talk about next is using those same jumper wires to do some more advanced testing. Testing where we verify how well the system is working. These are important tests that are going to let us find out how well the phasor itself is moving. Now, we've talked about the circuit. Now what we want to know is, once we have the right voltage, right current flow, is the phasor actually responding? Now, you can use bidirectional scan tool control if it's available. Use it. Here's what we can do. If we want to see if the phasor is moving, we're going to use the stuff we learned back in the training section to understand if the phasor is operating properly. We're going to observe the changes in engine speed for the phasor diagnostics. If the phasor is actually moving, it should make a difference. Now we're working on intake here. We're going to give you a section on intake. We're going to do the whole section over again for exhaust. But disconnecting the actuator will give full retard. So if you have a code identifying a problem that says it's over advanced, and we're going to talk about the symptoms, and those symptoms match up, disconnect the sensor or the actuator. It'll go full retard on the phasor. Grounding a ground side switch will give us full advance. So if this is the case, we're working intake and we get full advance. Advanced intake will give us valve overlap with the exhaust valve. If we have valve overlap, we will have EGR action, which will cause engine speed to drop and in some cases actually stall, depending on the vehicle. So grounding the actuator will give us full advance, should cause rough idle. If you had something saying it's retarded, you do this test. If it's a high side, we do very much a similar thing. High side B+ has to be applied to the circuit to give us full advance. Same thing, full advance, intake, we should get a big drop in engine speed. Disconnecting the solenoid will give us full retard, and we should see changes if that's the case. These are the codes you're going to be working with. If you get one of these codes, it says the position of the solenoid is wrong. P0011 is the intake, over advanced, bank 1. 21 is intake, over advanced, bank 2. 12 is intake, over retarded, bank 1. 22 is intake cam, over retarded, bank 2. Now we know how to react to these. Any manufacturer's code talking about over advanced, over retarded, we use the simple steps we just did. We advance it where it says it's over retarded. We retard it when it says it's over advanced, and we see if this engine changes. If it doesn't change, you got a phaser. What can keep the phaser from working? What are the root cause of bad failures? Oil pressure. It's got to be over 25 psi at 1500 RPM for proper phaser operation. That's not our spec. That's what several manufacturers recommend as their minimum oil pressure with variable valve control timing. Low oil pressure can cause erratic operation. Dirty oil, oil that's lost its anti-foaming capabilities, or oil that has the wrong specification can cause erratic operation, and the enemy of the phaser is sludge. Can't slide back and forth easily if it gets full of material. Sometimes this code can set if engine work is done improperly and the cam's not timed correctly. It's out of time. Follow the manufacturer's procedure when you do a timing belt change or you work on the phaser. And theoretically, crank and cam sensors that are erratic can cause false codes. Now, this is what all the theory says. We have never observed this, so I want to tell you it's possible, but we haven't seen it. Doesn't mean it doesn't work. Now, we need to match engine symptoms to codes. That gives us more information. It's always nice if we can match up the way the engine's running to the code we're working about. Over-advanced intake timing may cause idle to be erratic, depending on how far it's over-advanced, and cause stalling in some cases. Over-retarded intake timing will give you a smooth idle, but have low torque in the mid-range. Remember, one of the reasons for going to variable cam timing is to give a smooth idle, good mid-range torque. These two things, if it's over-retarded, over-advanced, one of these is going to be wrong, and it's going to match up with the code. Now, the symptom will vary by the size of the error in position. Use an enhanced scan tool if you have it to compare the desired to the actual cam timing. If you don't have a scan tool, use your multimeter. Does duty cycle hover around 50%? Remember we talked about that earlier. Use our quick phaser test to force the timing to max, advance at idle. The engine speed drops like an EGR is open or may stall in some cases. It's working. If not, replace the phaser if it's not working properly. Use bidirectional scan tool if you have one available. Here's what we're talking about, our quick test. We talked about it earlier. We're going to repeat it again. We're going to try to go to full advance. When a high side circuit needs B+ applied to be full advanced intake valve. When we fully advance it, it should cause the engine to change. If it doesn't change and you've got a retarded, over advanced code already, guess what? You just found the answer. Go fix the phaser. Low side. We need a ground to be applied to fully advanced timing. Same thing, just different situations. What we're doing here, remember, back to our training session. This is an example from the BMW Vanos. It emphasizes something. This only moves 12.5 degrees and may not be enough to cause the engine to stall, but you will hear the engine speed change when you advance this timing. So, this is the kind of phasing we're talking about doing when we have something that's over-advanced, under-advanced. Exhaust valves. We've got to do the same thing, except we have different criteria for exhaust valves. And we've got to talk about those. We've got the same type thing. Different banks, advanced or retarded. And we've said it and said it and said it, but sludge is the enemy of these systems. Same kind of diagnostics. Oil pressure should be over 25 psi at 1500 for proper phaser operation. Low oil pressure is going to cause it to be erratic. Dirty oil, oil that's lost its anti-foaming capability or has the wrong specifications, can cause it to be erratic. If engine work was done, make sure the cam was properly timed. And the crank and cams, almost the same scenario. But here's where our symptoms change. They're very different. Symptom will vary by the size of arrow and position, which we talked about before. Use an enhanced scan tool to compare the desired to the actual cam timing. Now, we get to an exhaust valve. Over-retarded exhaust valves may cause idle to be erratic and cause stalling in some cases, because now we're moving back into that overlapping with intake. We're getting EGR action. Over advanced timing will give you a nice smooth idle, but it'll have low torque at mid-range. These are exactly mirror image of the symptoms we had with intake problems. Now, we use our quick phaser test to force the timing to max retarded idle. When we're fully retarded, we expect to see the RPM drop like an EGR was open. Replace the phaser if it doesn't respond properly. Boom. It all works out in about the same way. So now we can diagnose position. We can diagnose the circuitry. We've handled all the codes in a very easy to understand manner. Now here is the summary to finish up talking about cam phasing before we move into valve lift. Variable cam timing requires two cams to time intake and exhaust separately. Some earlier systems had one of the cams and they used fixed timing like the Vanos. Some systems vary only exhaust timing like the Chevy 4.2 liter truck engine. Most single cam timing is done with the intake cam, but most of your newer vehicles are going to vary both of them, so they both change together. And one of the things we found confusing, we want to give you an alert heads up to, depending on what scan tool you've got. Sometimes you see information that says the letter A to identify the intake cam and the letter B to indicate the exhaust cam. Instead of saying intake and exhaust, they use A and B. I guess it saved a lot of ink not to have to put those extra 3 or 4 letters in there. But regardless, you now know how to diagnose it. Go over this as many times as you need to fully understand the diagnostics we're doing. They're simple. They're totally encompassing everything, the circuitry, the operation, and make sure it all works properly.